All right. Welcome back to campus. Hope you guys are all well, and we will take a look. All right. So today I want to talk about environments as well as scoping rules, and this is how R handles basically where objects are stored and how it retrieves values for the objects. Here is some related reading that I recommend. These are all from Hadley Wickham's Advanced R textbook, a great resource, so you should check that out. All right, so let's talk about binding and scoping. So all objects created and stored in an R session are collectively called the workspace. This is also known as the global environment, and that's basically where your objects live. When you execute a function, it creates a local environment. Objects that are created inside the function are accessible only from within the function, and objects created locally inside that function do not appear in the global environment. And so that's how R makes sure that execution of functions don't overwhelm your environment and things like that. Objects in the local environment will take precedence over objects in the global environment. So in particular, a global object that happens to have the same name as a local object, that global object will be masked by the local object with the same name. So the object name within the function will reference the local object inside the function rather than the global one. So let's just look at a very basic piece of code here. We say X, and then we have arrow C, 1, 2, 3. And so just informally, the way we think about this is we say we're creating an object X, and that contains the values 1, 2, 3. Now, technically, what's happening is that this assignment operator, that is the arrow key, but also the equal sign, associates or binds the name X to the vector 1, 2, 3. And there's actually two things that go on. We create an object in memory, a vector object in memory with the values 1, 2, 3, and then we bind the object, that object we just created, to a name X. Okay, so inside your computer's memory, there's now a set of values that have, this is vector, this object that has the values 1, 2, 3, and then the name X points to that thing. So the name or variable X is just a reference or a pointer, okay, to that vector. The name X points to the memory location on your computer that contains the values 1, 2, 3. Okay. All right, what happens here? So here I have X, and we assign to X the vector 1, 2, 3. Then we have Y, and we assign to Y X. And then we have Z, and we assign to Z the object 1, 2, 3. So what's the difference between Y and Z here? Okay. Well, variables in R, again, are references to memory locations of objects. So X and Y are two names that actually point to the same location in memory, okay? They're basically two names for the same thing. So it's kind of like a person having a nickname. So you can say, there's Tony, and we also call him, something else, right? Anthony, okay? So Anthony's his real name, but we also call him Tony. They're two names that reference the same person, okay? Meanwhile, okay, Z is another name, and it points to a completely different object. This happens to also have the values 1, 2, 3, okay? Also happens to have the values 1, 2, 3, but is a different object, and the name Z points to that different object. R handles all of the kind of memory allocation issues automatically, so you don't have to worry about this. This is kind of like, it's considered what we call a higher level language, meaning you have less to worry about the computer level stuff. Whereas Other languages like C and things like that, and its derivative C++, there's a kind of a lot of kind of memory management and stuff that you have to do there, right? You define these buckets that can store values, and then when you're done using that bucket, you have to kind of get rid of it, otherwise they persist and things like that. Whereas in R and also Python, there's like these garbage collectors that just kind of get rid of these things and clean things up for you. So you don't have to worry about it. But if you have a little understanding of some basic memory management, that can help in writing cleaner and faster code. Some of you might become software engineers, but the stats and data science curriculum isn't designed for software engineers. It's designed for data science, and so we don't have to concern ourselves so much with a lot of these memory management and computational efficiency things. But they are issues, and they are things that exist. Okay, R has what we call copy on modify syntax. Okay. So here we create an object X, and it has the values 1, 2, 3, or we bind the name X to the object 1, 2, 3. We also bind the name Y to the same object. And then in this line of code, we say Y subset 3, and we assign 4 to that. And so we're changing the third value in Y to the value 4. Okay? And then if I ask what is X, we might have expected that that the third value in X is also 4, but it's not, okay? If you did something like the equivalent of this in Python, it would change, but in R it doesn't. And R employs what's called copy on modify, okay? So when we modified Y, we said change the third value in Y to 4, okay? Before we did this, Y and X were two things pointing to the same object, okay? But then when we did this, R created a copy. R saw that we are changing the value of Y, and so it creates a copy and modifies the copy. So X still points to this original object, which contains 1, 2, 3. Now the value name Y points to a copy, a different object, and then that in that different object, this third value is the number 4. So R has what is called copy on modify. So when it sees you're going to modify something, it creates a copy of it, and it modifies the copy. So the original thing is unaffected. When we assign that binds a name to a value. Okay. Meanwhile, scoping is kind of the flip side, and that is how we find the value associated with a name. Okay. The scope of a variable is the region of the code where that variable is defined, where that name actually means something. Basic scoping rules are pretty intuitive. So if you look at this code, like I think we understand what's going to happen. So here we have Y is bound to the value 1 in the global environment. Okay, but we also create a function called G inside the and G is a function that receives the argument X. Inside the function G, we bind the value 2 to Y, and the last line of the function G says return the value X plus Y. Okay, so if I call the function G and I provide the value 3 as the argument, okay, what happens? Okay, well 3 comes in as the argument X. So X has the value of 3. In the next line of code, we see Y gets the value 2. And so it's going to return X plus Y. It's going to take the value of 3 for X, the value 2 for Y. It's going to return 5. Okay? And that's what we get. What is the output of G of 3? 5. And I don't think that's a surprise to anybody. Okay? R uses what's called lexical scoping. Okay? If R can't find a variable in the function's body, okay, it's going to look for it in the next higher scope. This is considered poor technique to reference objects that are not defined inside a function, but R does its best to find the value rather than return an error. This was a design philosophy that the creators of R decided upon. Okay, so actually, the history is that at Bell Labs, I don't know if you guys know about Bell Labs. It's kind of like, all right, I don't know, we're getting into just random history here, right? Like, okay, we have a lot of like innovation in terms of like machine learning and stuff, and that's happening at these big tech companies like Google and Meta and Apple and things like that. Okay, but if you go back, half a century, okay, to the 60s and 70s, okay, Google and Apple didn't exist, but the primary tech giant was Bell Communications, okay, and they'd had a lot of kind of advancing of technology, and they actually developed the computer language C and the computer language S, which is kind of the predecessor of R. And so C was designed for fast computation, and S was designed for kind of statistical work. And the design philosophy for S was let the people do statistics and not have to worry so much about computational efficiency. So those are kind of the diverging things. And so they employed things that the design philosophy of R and S and stuff like that is that, you know what, we're not, this is again not designed for software engineers, but just allowing you to kind of write quick scripts to get the work done. And so that might mean you're not going to have the best coding practices. Okay, so it's a bit of a double-edged sword. Lexical scoping makes our life a lot easier in that, like, we can have stuff and it's not going to error out, and R is going to do its best to figure it out. But also comes with the double-edged sword in that it doesn't require you to have the best coding practice. Okay, so in general, when you have a function, you don't want to really be referencing values that don't exist inside that function. But here it works. Okay, so here we have the value 1 gets, or the name y gets bound to the value 1 in the global environment. And here I have the function f. The function f receives the argument x, and the function f only has one line of code, and it's going to return the value x plus y. And so when I call f and I give the value 3, I provide the value 3 for the argument x. It comes in, and the function f executes, and it says, all right, I need to return the value x plus y. I have the value 3 for x, and now I need a value for y. And it doesn't have a value for y. And again, other languages would just error out and just say, hey, you didn't give me a value here. I can't do this, okay? R says, you know what? Let's do our best, okay? You want the value y? I can't find it here. I'm going to search. And hey, I look in the global environment. I find the value 1 for y. And we're going to take that. And so it's going to give us 3 plus 1, and f of 3 is going to return 4, okay? And it executes, it returns the value 4. And that's powered by what we call lexical scoping. Okay, let me give you your first answer. Your first answer today is the letter D. D as in dog. D as in dog. Okay. Variables defined within a scope only exist in that scope and only for the duration of that scope. If variables exist with the same name outside the scope, that is a separate object, okay? And it does not interact with the variables inside the scope, nor are they overwritten, okay? A function is its own separate environment that only communicates to the outside world via the arguments going in and the returned object going out. So for example, if you executed this command, and this is a terrible idea, you should never do this, but let's say you execute the command rm list equals ls. That's the command we write to delete all of the objects in our environment, right? That will only delete the objects defined inside the function's environment. It will not delete anything in the actual global environment, okay? There is the exception. There's something called super assignment. I have a few slides on that at the very end, if we have time to get to them. That searches the higher scope and the global environment, but that's considered a dangerous operator, and you shouldn't use that. But again, the key here is things that happen inside your local scope only happen in the local scope, doesn't interact with stuff in the higher scopes. So let's just look at this example. I have X, Y, and Z. They all get the value 1. They're all bound to the value 1 in the global environment, okay? I create a function f, okay? The function f, inside the function f, I bind the value y inside, bind the value y to 2 inside the function f. Inside the function f, I create a function g. And inside the function g, I bind the value z to 3, okay? Outside of the function g, or inside the function f, the very last line of the function f says return g. So it calls the function g, and it returns that. And so, what's going to happen? All right, so what happens if I call f, right? I call f from the global environment. I call f. Inside f, I take the value 2, and I bind it to y. And then I go down and I say return g. So we execute g. Inside g, we say z gets the value 3. And then return x plus y plus z. This is what it's going to return. So it looks for x, doesn't find x inside g, searches the higher scope, doesn't find x inside f, searches the higher scope, it finds x is the value 1 in the global environment. So x gets the value 1. All right, what about y? Searches for y inside here, doesn't find y. Okay, so it searches the higher scope, it finds y as the value 2, and it takes that. So y gets the value 2, and then it takes z. Searches for z inside of the current local scope. It finds z has the value 3. So it's going to do 1 plus 2 plus 3. Now, after we run f, what is it going to return? It's going to return 6. Are any of the values in the global environment affected? No, none of the values in the global environment are affected. All the values in the global environment remain 1, 1, and 1. So when I call what is f, f returns 6, 1 plus 2 plus 3. What is x, y, and z in the global environment? They're all still the values 1. All right, let's talk about environments themselves, okay? The environment is the data structure that powers scoping. The job of an environment is to bind a set of names to a set of values. And environments are treated as a bag of names, okay? Where each name points to an object stored somewhere else in memory. And the important thing is that bags of objects are unordered, right? So if I say reach into your backpack and give me the third object, that's like a confusing thing to ask for because the objects in your backpack don't have a natural order, right? Is the third object in your backpack like what is that, okay? Whereas a list, there's an order. I could say, what's the second item on the list? What's the fifth item on the list? That makes sense. But if you have a bag, like a bag of groceries, give me the second grocery item, okay, in your bag. It's weird, okay? That's weird. But anyway, this is what we have. We can create a new environment by calling new environment, and we're going to call this thing E. Within E, we can use $ notation for the names, and so I can say the name A is assigned to or bound to the value false. The name B is bound to the character A. The name C is bound to the value 2.3. The name D is bound to the vector 1, 2, 3. Okay, and so this is the illustration of the names getting bound to these different values. Okay, as with everything in our environments themselves are objects, the syntax to work with environment objects is similar to that of lists in that you can use the double square bracket and the $ along with names to get those values. You can ask what's the type of, the type is environment. To get the value of the name C inside the environment, you can do E $C, you get the value 2.3. E double square bracket, and you put in the name D, and you get the object with the vector 1, 2, 3. However, again, objects inside an environment are unordered, so you can't do something like E double square bracket 1 because there's no order. So you can't say what's the first object in the environment. You can ask for the listing of all of the names inside an environment by using ls. Okay, so you can do ls for E, give me all of the names inside environment E. If you don't provide an argument, you just get the names inside your global environment. Okay, that's the default is your global environment. You can also ask for ls.str, and this will give you a little bit more detail of the different objects in there. So this tells you what kind of values and the values that are actually in there, at least the first few. So unlike lists, the single square bracket does not work for environments. And then if you set an object to null, it doesn't remove the object. It keeps it, but now that name has the has the value null. Okay. So if you do want to remove objects from an environment, you use rm. Rm will remove the object. All right. Okay. Every environment has a parent, which is another environment. And in these diagrams, this blue dot with an arrow, okay, is the reference to this represents the pointer to the parent environment. Okay. The parent environments are used to implement lexical scoping. So if a name is not found in an environment, R looks for its parent. Okay. So here, if we search for A, it finds it here. If I search for D, it first looks for it in here, doesn't find the letter D or the name D here, goes to the parent and it finds the name D there, and it uses that object. Okay. Every environment has a parent, with the exception of the empty environment. The empty environment is the topmost environment with no ancestors. Okay. So we have a few environments that are special. The global environment, this is your workspace. Okay, this is the environment where you normally work. The parent of the global environment is the last package that you attached with library or require or something like that. It feels a little weird. I'll explain this in a moment. We also have the base environment. Okay, the base environment is the environment of the base package, and the parent of the base environment is the empty environment. So when you start up R, certain packages just get loaded automatically. And the base environment contains functions that kind of power the base functionality of R. Functions like C that allow you to create a vector. Functions like mean, okay? Functions like list that allows you to create a list. Some of the things, so those are functions that we need, and they exist in the base environment. And they get created when it gets loaded as soon as R gets started up. Okay. There's other packages that get loaded up, like package stats. Package stats contains other functions that we often use, but are related to statistics, like LM. We use LM to create linear model objects, and that gets loaded up automatically when you start up R, and that's in package stats. Okay. But anyway. So that's the base environment. The parent of the base environment is the empty environment. The empty environment is the ultimate ancestor of all environments, and it's empty, and it has no parent. Okay, and then the environment is just your current environment. So if you type out search, okay, this lists all of the parents of the global environment, and this is called the search path. Because objects in these environments can be found kind of in this workspace, and you can see all of the packages that just kind of get loaded when you start up R. And so it loads package base, the base package. I guess there's auto loads, package methods, package data sets, package utils, graphics, stats. In this case, because I knit, I had to load package knitter. But basically, these are all packages that kind of get loaded when you start up R. And then finally, you have the global environment. Okay. So the global environment, the base environment, and whatever, they're all in what we call the search path. And so as it looks for an object, it searches for the object's name in the global environment. If it can't find it, it searches kind of all of these packages that got loaded. Okay, until it reaches the base package, and that's kind of where the last place where it can look. And again, the parent of the base is the empty environment, but that's empty. Okay, so this is basically how R is going to search for some kind of object or some kind of name that you ask. So when you ask, you say you call LM, right, and you want to use LM. It's going to search the path, and it finds it. It's going to find it in package stats. Okay, There's other data sets that kind of get preloaded, so you can ask for like MT cars. I think that's like a data set or something, and again, I think that shows up automatically in package data sets. Okay. Now, every time you load a new package with library, so if you say library ggplot2, okay, it's going to load that package in between the global environment and kind of the latest package. Okay, and so that shows up now in the search path. And so now you can ask for ggplot, and it's going to find that function. Whereas before you loaded that, you ask for ggplot, it's going to say, I can't find ggplot. I don't know what ggplot is. So you load up the library. Now it's in the search path, and now you can find ggplot. Okay, so the parent of the global environment changes. Now, one consequence of this is that, let's say I say load up. I want you to load up package ggplot and dplyr and mosaic or something like that. All right. I say I want you to load up these packages, and you put those in. Now, if somebody else put in those 3 packages, but in a different order, their search path is going to be different from yours. Okay. So if they type out library mosaic first, then library dplyr, then library ggplot, their search path is going to be different from somebody who put in the thing else. Okay, so the search path is going to be different depending on how the order in which you load your packages. Okay, now a lot of times the environments that are created are going to be a consequence of using functions. Okay. There are 4 types of environments associated with a function. We have the enclosing environment, the binding environment, the execution environment, and the calling environment. Okay? The enclosing environment is the environment where the function is created. Every function has one and only one enclosing environment. Okay? As far as the other 3 types, you can have 0, 1, or possibly multiple. Okay? A binding environment is binds a function to a name, okay, using the assignment operator. That creates the binding environment. So the name where the function, reference to the function exists, is the binding environment. Calling a function is going to create an execution environment. The execution environment stores the values called during creation. That's the execution environment. And then when you execute an environment, the environment from where it was called is the calling environment. Okay, and I'll explain all of this in a moment. Okay, when you create a function, it gains a reference to the environment where it was made. This is the enclosing environment. That is the environment that's used for lexical scoping. When you name a function, the environment where that name exists is the binding environment. For 99% of your uses, the enclosing environment and the binding environment are going to be the same. Like, most of the time, you're going to probably create a function in the global environment. So your enclosing environment is the global environment. The name for that function exists inside the global environment, and that's probably going to also be your binding environment. Okay. So here's a function. Here's just a few lines of code. And this is an example. So we're working in the global environment. Inside the global environment, my first line of code, I say we're going to take the name y and bind it to the value 1. And that's represented here. The name y exists in the global environment. It points to an object in memory with the value 1. We also create a function f. The function f receives an argument x. And here's the code inside the function f. Because f was created inside the global environment, okay, its enclosing environment is the global environment. The name of f exists inside the global environment, so the global environment is also the binding environment. The enclosing environment is represented by this black circle, and the arrow that it points to is its enclosing environment. So this black circle points to the global environment. This is the enclosing environment. Okay, the name for the function exists inside the global environment. This is the binding environment. why do we have a binding and enclosing environment if they're going to be the same? Well, most of the time they're the same, okay? Sometimes they're different, and the times they're different is when you load up packages, okay? So remember I said the parent of whatever environment you're looking for in the search path is going to be different depending on the order in which I load up my packages and the order in which you load up your packages, okay? Furthermore, what if you create a function called var in your global environment, okay? That you shouldn't do that, but if you did create your own version of the variance function called var, and you call var, it's going to use the one that's in your global environment, okay? However, some functions are defined in terms of other functions. So, for example, the standard deviation function, the way it works is it takes the square root of the variance, okay? That's our definition of the variance, or of the standard deviation, is the square root of the variance. And there's basically another function in R called var, and it calculates the variance of something, and there's a little bit more. But basically the standard deviation just says, hey, take the square root of that. So what if you had created your own package, or you create your own function called var? Is that going to change the way the standard deviation function is going to work? Okay, because the standard deviation function is going to find this, look for var, and we obviously don't want that to happen. We want the standard deviation function to work consistently no matter what order in which we call our libraries, no matter if I've created a function called var or not. Okay, we want it to work the same way. So the way R ensures that is it uses what's called the namespace. This is going to be the enclosing environment. Okay, so the distinction between enclosing and binding environments is important for functions inside of packages to ensure that every package works the same way regardless of what packages are attached and what order in which they're attached or whatever requires an internal environment called the namespace. This is the package where the functions are defined, or basically going to act as the enclosing environment. Every function in a package is associated with a pair of environments: the package environment, which is basically its binding environment, and the namespace environment, which is going to be its enclosing environment. So the package environment is the external interface to the package. This is the environment that R loads in the search path, okay? Which the R user uses to find functions in an attached package. Its parent is determined by the search path, and so as far as the package environment goes, that could change. The parents of those things could change depending on the order in which you load your packages, okay? The double colon operator is used to find a function directly from the package environment regardless of the search path. So we have the function mean, which exists in base, and you can reference that function by doing base double colon mean, okay? There's another package called mosaic, and inside the mosaic package there's a function mean, and if you want to use that function, you call mosaic double colon mean and things like that, okay? So the double colon will reference that. It's kind of like using a first and last name, right? So to make sure that we're both talking about the same person, we might use their first and last name, okay? And it only feels strange to use a first and last name if it's kind of like, well, that's the only person with that name anyway, right? But just to make sure we're all talking about the same person, we can use, package double colon mean, first and last name type of thing, okay? So the double colon notation allows you to access objects that might be masked by other objects from packages higher in the search path. Okay, the namespace here is the internal reference to the package, and this is how we find functions and how it works. So this black dot points to the enclosing environment. The enclosing environment is the namespace, right? And so this is going to make sure that when it looks for variants and stuff, it's going to search the enclosing environment for namespace. Whereas the package environment, this is the binding environment. When we search for the function SD, it searches for it in the package environment. All right. Okay, let me give you your second view quiz answer. Second answer today is the letter A. A as in apple. A as in apple is our second answer. All right, every time a function is called, a new environment is created to host the execution. The parent of the execution environment is the enclosing environment of the function. So basically where that black dot is pointing to, or where the function is defined. Once a function is executed or is completed, this execution environment is just thrown away. Right? So let's look at a very simple function. This function is called h. The function h receives an argument x. Okay. The first line of code takes the name a and binds it to the value 2. The last line of code in h returns the value x plus a. It's going to take the value x that it received, add a to it, which has the value 2, and return that. Okay, so we are going to call h with the value 1 and assign the result to y. Okay, so y is going to get the value 3. No big deal. But let's just see what happens when we do this. When we call h with the value 1, okay, this immediately creates an execution environment. Okay, and before it even reads the first line of code in the body of the function, it defines the execution environment, and then it sets up all of the names in basically all of the arguments that come in. It binds those values in. So within this very first thing where it says h of 1, the very first thing it says, okay, let's look at the arguments that came in. The name here is x, and x is going to get the value 1. Okay, and it creates this, what we call the execution environment right here. The value name x gets bound to the value 1. That happens even before it reads the very first line of code. Okay, h exists. This would be, I guess, our global environment. Okay, the enclosing environment of this function is the global environment. Okay, the binding environment is where the name exists, also the global environment. Okay, but the very first thing, as soon as we call it, okay, h of 1, that creates the execution environment, takes the name x, gives it the value 1. Then it reads the first line of code. First line of code says, take the name a, give it the value 2. So this is the next thing that happens. The value of a gets bound to the value 2. Then the third line of code says x plus a, so 1 plus 2, all right, and return that. Okay, so that's going to return, and so the R is going to return that value. As soon as it returns the value, this execution environment poof disappears. It is gone. Okay, so it returns the value 3, and it's going to get bound to the name y. Okay, so the name y now gets bound to the value 3. The function completes. It returns the value 3. That execution environment goes away. It's now bound to the value name y. Okay, so when you call it, it creates the execution environment. Then it starts reading the lines of code. When it hits that last line, it returns the value, and then that environment goes away. So that's what happens. When you call a function, it creates that execution environment. The execution environment has two parent environments. It has the enclosing environment, where the function is created, and that's and then it also has the calling environment, which is the environment from which the function is called. If you create a function in the global environment and you call a function in the global environment, then your calling and enclosing environment are going to be the same. But sometimes we call a function from inside another function. In that case, the enclosing and the calling environments could be different. The normal scoping rules always use the enclosing environment. So when it looks for a value, it's going to search the enclosing environment. Okay. R also supports what is called dynamic scoping, and you can look for values in the calling environment. That uses the function get. So let me just show you an example of this. All right, so here I have x is 0 and y is 10 in the global environment. Inside the in the global environment, I create a function f. Inside of the function f, we give the value x2 and y gets the value 100. And inside of f, I create a function h. So the enclosing environment of h is f. Okay. Inside h, x gets the value 50, and h is going to return x plus y. Okay. All right. So if I call f, what is f going to return? Okay. So if I call f, we get x is 2, y is 100, And the last line of f says return the value of h. So we look at h. H says inside h, x gets the value 50, return x plus y. So we're going to do 50 plus y. We look for y. We search the enclosing environment. Enclosing environment is f. So we're going to get y is 100. So we're going to do x is 50 right here. Y is going to be this value of 100. H is going to return 150. And so this returns 150. That's the last line of f. F is going to return 150. Okay. And we have that. Okay. So in the description is there. So, all right. That's okay. We get a value of 150. Okay. Here, what happens here? So x is 0, y is 10 in the global environment. We have a function g. We have a function h. They're both defined inside the global environment. Here I'm going to call h. What is h going to return? So h says inside h we give the value x3. Okay, so 3 gets assigned to x, and then h is going to return x plus y. Okay, so x, this value of x has the value of 3, and then we look for y. H is defined inside where? The global environment. So we're going to search the global environment for y, and we find the value 10. So when I call h, it returns 13. Okay. All right, what about g? When I call g from the global environment, what's it going to do? I call g from the global environment. X gets the value 2. Y gets the value 100. And then we call h. All right, so the last line of g is going to call h and return h. So we call h. Inside h, x gets the value 3. So we have x is 3. And then it looks for y. Where is h defined? H is defined in the global environment. So when we search for y, we find 10 in the global environment. Okay? And so this is going to return 13 as well. So when I call h, I get 13 from the global environment. When I call g, okay, I'm also going to get 13. Okay, that might feel a little bit weird, but that's indeed what I get. If I call h, I get 13. What happened? Why is that not working? Okay. G gives me the value 13. Okay, so h gives me the value 13. G gives me the value 13. Okay. A little bit. So these notes, as a good practice for you, is as you review these notes and you see this thing, question here, pause and see if you could figure it out before you go to the next slide. All right, make sure you understand, check your understanding, make sure you can answer these things. Okay, here we have dynamic scoping, and in dynamic scoping, we are going to get the value from the calling environment. The calling environment, not the environment where the function is defined. So here, when I call h, I'm going to call h from the global environment. So my calling environment is the global environment. Inside h, x gets the value 3. Y, we say get y environment parent frame. It's going to use the calling environment. Y is going to get the value 10 from the global environment because we called called this function from the global environment. So y gets the value 10. This is going to return 13. We're going to get 3 plus 10, and we get 13. Okay. What about when I call g? Inside g, x gets the value 2, y gets the value 100. Then we call h from inside of g. When we call h, x gets the value 3, and then we say y, get y from the parent frame, the calling environment. So now, even though h is defined in the global environment, because it was called from inside of g, we're going to get the value 100 from inside of g. And so now, this is going to have the value 3 plus 100, and calling g here is going to return 103. So h gives me 13, g gives me 103. All right. Yes, question?
So if you hadn't put the get in the h function, when you called it in g, would it have taken the y from the global environment?
Yeah. So the question was, if I didn't include this line about get y here in the parent frame, it would have taken y from the global environment and gotten 10 and given 13. And that's exactly the code that we have on this slide. Okay. So this slide's code is exactly the same as this slide code, with the exception of here I have the get line. And when we put in the get line, we get 13 and 103. When I don't have that get line, I don't know why that slide is disappearing, we get 13 and 13, okay? Okay, so my very last set of slides are on super assignment, and and this whole section is just basically don't use super assignment, okay? Don't use super assignment. But let me go ahead and give you your last view quiz answer. Third answer today is B, B as in bear. B as in bear. B is your third view quiz answer. Okay, so super assignment is this basically double arrow, right? And sometimes you will see it exist in other people's code. But you yourself, you should probably never use super assignment. Okay, so the regular assignment operator creates objects in the current environment. The super assignment doesn't create it in the current environment, but modifies an existing variable in the parent environment, okay? Now, if it doesn't find the existing variable in the parent environment, it keeps climbing the scope ladder until it reaches the global environment. If it reaches the global environment and can't find it in the global environment, it will create an object in the global environment, okay? But again, don't use super assignment if you can avoid it. All right, so let me just show you the basics of super assignment. And this example is simple and you feel like, wow, that doesn't seem so scary, but it can lead to problems. All right, so here, x, y, and z all get the value 1 in the global environment. Inside the function f, when I call f, the first line of code says super assign 3 to y. So this is going to look in the parent the enclosing environment of f, which is going to be the global environment, and it's going to modify the value of y to 3 in the global environment. And then it says return y. It searches for y. Y doesn't exist in the local environment, okay? But it does exist in the global environment, which has the value of 3, and it's going to return 3. So when you call f, you get 3. If you ask for what are the values of x, y, and z in the global environment, you get 1. Y is now 3, and z is 1. Okay, and you go, oh, okay, well, that doesn't seem so bad. It can become bad, okay? Here, x, y, and z have the values 1 in the global environment. Inside the function f, I super assign 2 to y. Again, this modifies the value of y in the global environment. Inside f, I define a function g. Inside g, I'm super assign 3 to z. Again, it searches the higher scope. It doesn't find z in f. So it searches the higher scope and it finds z in the global environment and it modifies that. Okay, so z is going to get the value 3. Then it says returns x plus y plus z. It searches for x, doesn't find it here, doesn't find it here, finds it in the global environment, takes value 1. Searches for y. It's not in g, it's not in f, because remember this modifies it up here. So it takes the value 2 in the global environment. What about z? Doesn't find it in here, doesn't find it in here, but it finds it in the global environment, gets the value 3. So this is going to return 1, 2, 3, 1 plus 2 plus 3, returns 6, and everything in the global environment has been changed. So we're going to get 6, and if I ask what are x and y and z in the global environment, they are now 1, 2, and 3. Okay. What about this? Here, this is even weirder, okay? X, y, and z are 1, 1, 1 in the global environment. Inside of f, I say y gets the value 2. But then I super assign 4 to y. Now this thing skips the y that exists here and goes straight to the global environment. The global environment y gets changed to 4. Okay, inside of f I define g. Inside g we say take the value 3 to z. Looks for z inside here. There's no z inside here. Searches the higher thing, it finds z inside the global environment, and it's going to change that. Z gets 3. So in the global environment we have 1. We have 4 for y, z is 3. But we ask for x plus y plus z. It searches for x. No x in g, no x inside of f. X is 1 in the global environment. Searches for y. Y doesn't exist here. It does exist here and it has the value 2. So y has the value 2. Z searches for z. Z is in the global environment. So it's going to do 1 plus 2 plus 3. It's going to return 6. But in the global environment we have 1, 4, and 3. Okay, I'm out of time, but you can see some more examples of how weird stuff happens, and take a look at that. All right, so we'll wrap things up here. Have a great rest of your day, and we will see you on Friday.